So, in signal processing we will often have to encounter with limits, sequences of functions, series summations, and in fact each term in the series could be a function, so on and so forth, right, functional series, etc. And there are also these notions of continuous functions, discontinuous functions, and we need some treatment into this. So, the root to these ideas stem from analysis in mathematics. I will not delve too much into analysis because it is a separate course in itself in the field of mathematics, and you could do a rigorous course for 30 hours as part of your NPTEL. But I will just briefly give you some ideas about continuity, convergence, etc. As part of the discussions here, which is going to be useful in your understanding of some of the signal processing ideas. Okay, let us first talk about continuity and forms of continuity. Right. Now, consider S to be a subset of real numbers R, and F is a mapping from S to R, and this is a real valued function defined on S, right. There is some subset S of real numbers, and there is a mapping from this subset to real, and this is a real valued function defined on the subset S. So, S, for example, if you think of S as say 0, say 2, this is basically all x belonging to the set of real numbers such that 0 is strictly less than x less than 2, that is, it is open on both sides. It can be infinite, like S is 0 infinity, which is basically x belonging to R such that x is strictly positive, right, because 0 is not included, it is strictly positive. So, we may encounter many such type of these sets. So, let us start with a notion of what continuity is. So, I will start with the definition. For some function to be continuous on this subset. Okay. The function f is said to be continuous on S if and only if and only if for every x naught belonging to S, for every epsilon which is greater than 0, there exists a delta which is greater than 0, which depends upon x naught and epsilon. For every x belonging to this subset, the following holds that is if x minus x naught absolute is less than delta, this implies the absolute value of f of x minus f of x naught is strictly less than epsilon, and it is not continuous on S if this is greater than or equal to epsilon. There is a notion of, I will go to the next slide. There is a notion of uniformly continuous. So, I call this concept as uniformly continuous. So, the function f is uniformly continuous on S if and only if for every epsilon greater than 0 there exists delta greater than 0. That means delta is depending only on epsilon, right, and then you choose points x naught belonging to S and x belong to S, choose these 2 points. If absolute of x minus x naught is less than delta, this implies that absolute of f of x minus f of x naught is strictly less than epsilon. Now, you have to sort of be careful how the definitions are worded very carefully. So, in the case of uniformly continuous, you choose first an epsilon greater than 0. So, I will just write it down in red here. So, we choose epsilon greater than 0 and we let some delta, which is basically delta which is a function of epsilon, then you choose x naught belonging to S and x belonging to S. You assume that the absolute value of x minus x naught is less than delta, and this implies that absolute value of f of x minus f of x naught is less than epsilon. This is the English way of writing things. This is a little more mathematical way of writing things. So, I think you have to observe very carefully that in the order, I first for every epsilon greater than 0 I choose delta which is greater than 0, and this delta depends upon epsilon and not really on the point, right. So, just going back one slide where we define continuity property on this subset. So, here the difference is as follows. So, here we choose x naught belonging to this subset, then we choose epsilon which is greater than 0 and we let delta which is basically a function of both the point x naught and epsilon. Observe this very careful point that it has to depend on this x naught, on this point, delta depends on this point, and then you choose some x belonging to S and assume that x minus x naught is less than delta, and if you assume this with all these conditions, this implies the absolute value of f of x minus f of x naught is strictly less than epsilon. So, at least we got an idea of what is continuous and what is uniformly continuous, right. Let us look at some examples towards this understanding. Okay. Let this subset be the real line itself. Choose the mapping to be mx plus c. Okay. Let us examine if f is uniformly continuous on S, right. So, what do we know, what do we need to do here? So, first we choose some epsilon which is greater than 0, because we have to examine uniform continuity. So, we first choose some epsilon which is greater than 0. Let delta be epsilon upon m. I will tell you why we choose this m. I mean, at the moment just trust me and things become very clear. Choose x naught belonging to R, choose x belonging to R, assume x minus x naught is less than delta. Now, consider mod f of x minus f of x naught, this is mod mx plus c minus mx naught plus c, which is, so I will assume that m is just to make things a little easier, I will assume m is greater than 0 and m naught equal to 0, so that this is taken care of. Now, this is m times mod x minus x naught, and this quantity is, if this is basically m times delta, and this is strictly, this is quantity strictly less than delta, right. So, I can say this is quantity strictly less than m times delta, and delta is epsilon upon m. So, therefore, this quantity modulus of f x minus f x naught is strictly less than epsilon, right, and that is the reason why I chose delta to be epsilon upon m. So, now you can see the choice of delta equals epsilon upon m, why it has been carefully chosen, right, and this is satisfied. Therefore, f, this function which is a mapping from S to R is uniformly continuous. Okay. Let us take another example. Suppose S is given by x belonging to the set of real numbers such that 0 is less than x less than say some 2 and f of x equals x square. Let us examine if f is uniformly continuous on S. So, it is straightforward, let us just work through these steps here, right. So, what we have to do is we have to choose some epsilon which is greater than 0, let delta be epsilon upon 4. I will tell you why this thing appears like this. Then we choose x naught belonging to S and x belonging to S. Okay. Now 0 is less than x naught less than 2 and 0 is also less than x less than 2. Therefore, if I add these two intervals, 0 is less than x naught plus x, this is less than 4. Okay. Now, let us assume the absolute value of x minus x naught is less than delta. Now, consider mod f of x minus f of x naught, in this case is x square minus x naught square. You can factorize this as x plus x naught into mod x minus x naught, because x plus x naught is basically definitely greater than 0, right. We know this quantity, therefore, I did not put the absolute here, and this is basically 4 times I would say this is basically 4 times mod x minus x naught, and this is basically less than 4 times delta, and therefore, this is, if I choose delta to be epsilon upon 4, this basically satisfies the condition that absolute value of f of x minus f of x naught is strictly less than epsilon. Okay. So, this is again uniformly continuous. Well, there is a small catch here because the range is from 0 less than x less than 2, precisely x plus x naught will be strictly less than 4. So, this equality here would have to be an inequality which is strictly less than, I mean, this is something to note. In our examples on f x is m x plus c and f x is x square, that is, we consider a linear function, we consider a quadratic function, we landed up with a situation where mod f of x1 minus f of x2 is less than or equal to some m times mod x1 minus x2, right. We landed up with a situation like this for all x1 x2 belonging to S, right. Inequality of this form is called Lipschitz inequality and the constant m is called the corresponding Lipschitz constant. Okay. So, this is an important note. I think we understood what this this idea of continuity is, what the idea of uniform continuity is. I gave you examples of uniform continuity. I will give you some homework exercises that you would want to work. First, examine if f of x equals x square is uniformly continuous on the interval s, which is basically 0 to infinity, and it is basically an open interval. So, this is one exercise that I would want you to try, and the second would be examine if f of x given by 1 if x is positive, 0 if x is less than or equal to 0 is continuous. Of course, you know the answer to the second problem because there is a jump here, right. I mean, it is like a step function, there is a jump here and you know it is a point of discontinuity, but using the definitions that we learned just now on continuous functions and uniformly continuous functions, I would want you to examine if this is continuous or not. Okay. So, I think with this we cover the essentialities of continuous property. Then next we will talk about convergence, and then we will discuss some of the subtle issues related to convergence of sequences and then convergence of functions, which is essential for your signal processing understanding. Thank you.